Well, good morning, everybody. Welcome to the last session of the invited speakers for SC19. My name is David Abramson. I'm Vice Chair of the SC19 Invited Speakers Committee with Manish Parasha. So it's been a fantastic couple of days with what we'll finish with is 12 invited talks today, and I think you'll agree it's been a very nice spread across applications and technologies. So we have two speakers today in this theme. The first talk is going to be given by Dr. Ilkay Altintas, who's the Chief Data Scientist, Science Officer at the San Diego Supercomputing Center at the University of California, San Diego, where she is also the founder and director of the Workflows for Data Science Center of Excellence. And she's a fellow of the Halseyoglu Data Science Institute. And Ilkay, who's Turkish, can come up here and pronounce that correctly for me. So thank you very much, Ilkay.
Thank you. Good morning. So I'm Ilkay Altintas, and it's pronounced Halıcıoğlu Data Science Institute for the curious. I'll talk today about the work we've done with wildfire communities over the last couple of years. But what led to it? I think very few of you here remember what you've done on October 26, 2003, as vividly as I have been. I was at a meeting on a Sunday in Santa Barbara with some ecologists for NSF-ITR-SEEK project at that time. Around 10 a.m., I receive a call from my now husband, and he says, "Be careful, there's fires out there." I didn't know what that meant. It was my first experience of California fires. And it was before smartphones and Twitters and all of that. So I didn't know until the evening, until I got out. My train to go back home was canceled. I got on a colleague's pickup truck to go back to San Diego, and one side was sunset, one side was fire. So it made an impression. So that one was Cedar Fire. And it costed us 17 lives across San Diego. More than 500,000 acres were burned, and many structures and more than $1 billion in economical costs. Since then, it's been 16 years. The black parts are the burned areas across the United States. So fire is a problem, but in California, it's a bigger problem. It's a growing problem. In the last 16 years, we had 13 of the 20 most destructive fires in California's history. And every year, we have the next most destructive fire in the last couple of years. So the trend is these things are growing. They're becoming more and more frequent. And they're caused by human activity mostly. Power lines, human activity, arsonists, those are the main causes of fires. Just to name a few, Woolsey Fire, which was last November during SC19, and I was actually working in the trenches with my team in the evening to help some of our first responders. And Camp Fire was, the most devastating fire with 85 lives lost. There's a huge economical impact, but we are also losing lives and property and many other things that we care about as humans. And come fall 2019, it's everywhere. Every day I open the newspaper, there's something about fires, about the shutdowns, about insurance policies, about how a new fire is happening or being managed. So this is very much a part of our lives now. We live with fire, and we need to do something about it. So how can technology help? We need to understand, first of all, why they are happening. In California and many places that these fires are happening, we are actually living in what we call a fire-adapted ecosystem. So the ecology needs that. In California, some plants won't seed, some things won't happen that keeps our ecology healthy and safe for the ecosystems living in it. But what happened is in the last 100 years, the suppression policy is we put down any fire we can. And there's a huge biomass and fuel buildup that relates to these fires. And the climate is changing, the temperatures are rising, the weather is changing, And what we've done is we also built our homes, what we call at the wildland-urban interface. So we live where these fires are bound to happen, and we suppress them. They are very weather and fuel dependent. So on a regular weather, this is our regular day in LA. This can happen, and if there was a fire in that ignition point with a red marker, it's a little harder to see. It would be, a fire that we can control. On a high weather day, high wind, low humidity day, Santa Ana weather for us, the same ignition point would lead to a fire. And I don't know if you can see this, but the population in the first one, it is like 12 people and it's manageable. In the other one, it goes to 4,000 acres and 9,500 something people with number of houses growing in the path. So the thing is, what I showed you is some models of what the fire would behave like. So it can be modeled. There are different types of fire models. There are operational use models. And there are simplified models, reduced order models at times that you can compute really fast, and you can run numbers of ensembles for different situations. And there are also models that are more CFD-based, computational fluid dynamic-based. They're to understand fire physics. They can be coupled with atmospheric models. So you can model this behavior in the short term for initial attack or the current planning purposes, mitigation purposes. And you can also model things like understanding climate's effects and other effects in the long term for planning. In 2015, through the WIFIRE project that I'm going to talk about, we ran a workshop on how can we actually bring fire modeling more towards operational use and planning and other purposes. So the workshop report is available if anyone's interested. And the fire behavior triangle, we call it, you need some data about topography, weather, and fuels, which is the biomass that burns in the path of the fire. And the data comes from different sources. Right? You need to have, when we call data-driven fire modeling for operational use, which is mainly what I'm going to talk about today, you can get weather forecast data. You can get ground-based weather and camera imagery. Land cover and fuel information databases are published on that, although some of them are outdated and less detailed than we'd like to have them. The landscape data, what is the topography? Fire perimeter gets published on a regular basis, and you can use that to understand the effectivity of models and things like that and adjust these fires, the models themselves. But what can also be done is make use of remote sensing, so we can bring together, things that are streaming from satellites, drones, and aircraft into these models. So when there's this much data from this many sources, what we need is actually an infrastructure, data as infrastructure, to first of all enhance and accelerate fire science, so we can make the data available in forms that models can ingest, and both science and operational use can take advantage of. So the need when we started in essence was, can we have an integrated infrastructure to catalog these data sets, curate them, make them really good data sets for modeling, analyze them, make them findable, and communicate them, visualize them, both for fire science and also potentially at that time for operational use. This is where the WIFIRE project started, with the idea that we can do this. We can actually create a test bed for anyone who wants to do this. And the project was supported by NSF from 2013 to 2018 to build a cyber infrastructure. So the National Science Foundation is the only place who can fund something like this. It was very research-driven. It was very risky at that time, and it was about building cyber infrastructure to conduct science. And what we were hoping to achieve, and I'm happy to say we did, is to bring the data through a communication layer to workflows that can ingest this data and take advantage of models, scalable computing, and put them in a form that we can communicate to different platforms for different audiences to make use of the insights gained from the data. So little known thing about WIFIRE is it's an acronym, and the W in it is workflow. So it was very much around these dynamic automated workflows for taking the data, making it useful, cleaning it up, curating, and communicating the results. So what's the innovation here? It's a combination of that curation concept, data management concept, data science concepts in it with fire science, and automating, bringing this big data with fire modeling dynamically at a scale that these models need to run in, and as dynamic as the applications and the use of those applications demand. So what are the products of the WIFIRE cyberinfrastructure today? It's that data infrastructure that we were talking about, taking any data related to wildfires, sort of taking them through a funnel to make them fair, findable, accessible, interoperable, and reusable, so the fire science community and other interfaces can take advantage of this. The other part of it is modeling services. Can we actually take scientific models built by the community and turn them into services that can be run for different purposes? And some of these will be for fire response in the scenarios I'm going to talk about today. Some of them can be for understanding fire physics and seeing the effects of different atmospheric conditions on these models, very much from a science perspective and less from an operational use perspective. And the other things the environment provides is automated modeling workflows and machine learning pipelines for different parts of the infrastructure and data sets that can be communicated for any infrastructure who wants to make use of these data sets. But the one that I'm, I think, most surprised and maybe proud about is this growing community of 130 plus organizations who are taking advantage of these services one way or another. Not just for operational use, but for planning, for bringing evacuations, for bringing aid to the people in the path of the fire, for managing how utilities are creating fire policies and things like that. These 130 plus organizations and our partnerships with them led us to actually build the future together, come up with this public-private partnership concept, and turn the project that was funded by NSF into a self-sustained lab called WIFIRE Lab at the San Diego Supercomputer Center, with partnership from the rest of the UCSD organizations. And I think what we are now doing is we have 3 arms in the lab. One is the research arm, one is the operational arm, and the other is the product arm that can actually operationally create these software modeling data products and run them for sustainability. So back to 2010. We actually started before 2010, but in 2010 we were like, okay, can we now do what we are doing for the community to accelerate data-driven fire science? I think fire science had to have some more data concepts in it at that time. And there was all these big data concepts growing. We were building a number of different tools for big data. We were monitoring data coming from sensors. Maybe we were visualizing them, but we weren't yet using them in a dynamic fashion in the concept of models. So early enablers there, and another National Science Foundation project, High Performance Wireless Research and Education Network, HPRAN, was funded since the early 2000s, and it built weather stations and environmental sensors on a network in the back county of San Diego when internet wasn't there. So it's a wireless network, and over time they also built mountaintop cameras. So on a fire, it was the only situational place that the responders can go and look at the fire and gain more situational awareness and understanding of how the fire is doing. I'll show some examples of that. And the other thing was Farsight, which was an operational tool that was built and used by US Forest Services and other organizations. And it was a model that we could actually use in an open source fashion and turn it to be a dynamic data-driven initial attack tool using these data concepts. A very simple use case here is, for instance, the Santa Ana conditions. In the Southern California, in San Diego, Los Angeles, the Santa Ana conditions cause these major, what we call uncontrollable or very destructive fires because we only let them burn and remember when we actually, when they're unstoppable. The suppression is very good, but the behavior of the fire changes drastically when these winds are happening. And Santa Anas are defined by high wind speed, low humidity, and the direction coming from desert towards the ocean. And HPRN had those weather stations, and our energy company, SDG&E, actually installed 160 plus more on them in strategic locations, so we can understand the weather in San Diego at a high resolution, and based on that, we can model that. And HPRN was generating alerts when any of these sensors receive, I don't know if you see those yellow pins, so any of these weather stations receive a data or condition that points to a Santa Ana weather. But, you know, it's just one station, and it doesn't mean the rest of the county is being affected by that. So then how can we model what we are seeing, and to see the effect of it, really what parts of the county is affected by that? So what you can do is model actually wind when you have one of these conditions. And every 10 minutes, you can look at how the winds are doing. And based on that, you can actually use typical parallel computing, embarrassingly parallel computing techniques to actually run these models for the rest of the county. But then what needs to happen is the products of those models need to be viewable on a map if we are going to generate alerts from that. So you can add some GIS concept at the end to turn those into things that you can put it on a map. So what happens then is instead of just those yellow pins, you can alert in a more focused and purposeful fashion to the red zones, because it happens that after you model the wind, you understand that only those red areas are affected by those Santa Ana conditions, and you can direct the purpose of these alerts in a way that, you know, only the affected people can receive them. So this is a very simple depiction in a model, early model that we worked on, but our energy company actually picked this concept, and what they have done is they created a fire potential index by a high resolution weather modeling at 2 kilometers. So for 3 weeks ahead now, they can see the fire potential is rising or coming, and they can alert the authorities. And when you have something like that, you can plan the resources accordingly. So what we've seen in 2003, Cedar Fire, it was a big devastation due to lack of organization at times too, and communication. A lot of them can actually be improved. So what happens during a fire? You'll be surprised to know when there's a fire, the biggest question is, where is the fire? Almost no one knows that, because it's moving. It's not just one point, it's a whole area, and it's constantly changing. It needs measurement, and there is no large-scale infrastructure to measure the growth of the fire as it's happening. And when you have that information about the local environment and the behavior models, you can also know, if you know where it is, you can model where it will be in the next, let's say, 1 to 6 hours. So what we do in WIFIRE is we take advantage of all the data sets, the weather data, landscape data, fire perimeter, fuel information that I mentioned, and it goes into workflows that can run ensembles of models for initial attack, in this case Farsight, and generate maps that shows this growth to the right people who has to have this knowledge in their hands. We don't stop there. Remember, I said nobody knows this information. There are lots of things you can do by measurement, and one of the things you can do is, let's say, run an aircraft over it, or get some satellite measurements that in higher resolution when you have them, and understand where the fire front is, so you can observe the fire front, and you can adjust the models at each iteration, so whatever the model didn't take into account, you can actually make up for it with the measurement and data. So let's say you have an initial perimeter, you modeled it 2 hours ahead. This is the black area is the perimeter. In 2 hours, maybe you got the next black area here, the grayish area, as a perimeter. You can do adjustments to the fire models, and then model from that point to the next 2 hours using those adjustments. This is all nice and great, and why is it important? Because fire behavior is changing. Fire NATO is a word. and models to capture what's going on depends highly on the dynamic environment that the fire is creating itself with the effects of the wind and fuel and things like that. So no behavior model will be able to tell exactly what's going on or take advantage of that. But if you adjust it with real-time information, the models become more and more accurate over time. And we built these techniques. We were doing the research and development to make these workflows production ready and things like that, but we didn't have real operational users. We were being advised by operational users, but we didn't have operational data for that critical bit of, can we get that fire perimeter from the aircraft and run these dynamically moving models. Year 2015, LA fire chief calls me and says, we can use this. And it was interesting that we went up there, and when I got that call, I was actually trying to write a grant, 50,000 grant, to fly a plane over fires happening at that time, because we didn't have that real operational fire information, and we badly needed that data. And every time we asked, we were like, oh, you'll never get that type of data. It doesn't exist. And he saw the need, and he said, I'm going to put this in my workflow. I'm going to have a fire chief on the aircraft, on the helicopter, and you'll get those perimeters. That was the starting of a very fruitful partnership there. And what happened is we went to LA Fire Department. This is the pictures from our first meeting. That's me on a helicopter, terrifying. And we were showing these techniques. We were trying to explain data assimilation and what that means and things like that. Data uncertainty, when we get that, what that uncertainty means. But we didn't have a way to make it useful in the context of their operations. FireMap is a tool that the idea of it was born that day. Even if when we said in our original proposal we'll make these interfaces, there was no user for us to build those interfaces for and to understand how they would use it. So FireMap tool, in essence, is built on the computing infrastructure, data, and workflow services WIFIRE had, but it added this layer, web-enabled layer, to view the data and to do modeling on the fly. It was used in many operational fires, and typically what you see when you come to FireMap is all the information related to it. Fuel layers, cameras, weather stations, satellite readings, and other operational things that can be related to the fire. And you can create an ignition point, or you can ingest an ignition point or a perimeter from data sources, and environment models enables manual modeling of it. And there are some workflows that we are building now to do these automated continuous models as well. So what you see here is a model that shows every half an hour growth of fire with different colors, and ETA and population it's expected to hit, and things like that. So one of those sources are the HP ran cameras. Now they're also inspired another effort called Alert Wildfire with pan-tilt zoom cameras. You can go and actually zoom into these fires and do early detections and things like that potentially. So if you clicked on a fire day on one of these cameras, and you could see the streaming information from the cameras through WiFire, you would see something like this. You would actually go to the HP ran infrastructure, and you would see these different behaviors of the fire. There was a fire at this ignition point, and this is the final perimeter of the fire. This is the San Diego Peak West, which has seen that fire. And if you actually went to that ignition point on a clear day, it would be here on the camera. And we can actually click on that camera image and get that ignition point into FireMap as well. So, and then once you have that ignition point, you can parameterize and model the fire. But that night, when there was fire, when you went to HPRAN, this is what you've seen. And the smoke and the fire can be detected on that image. And once it's detected, it translates into something like that in my fire. Remember that ignition point I saw, the red marker? This is where those red spots are. And those red spots there are the satellite detections. So one of the NASA MODIS or WIREs went over this, or both, and they detected fire in that area. But by nighttime, when you see what's going on in the camera there and those ignition points, it comes close to, it's growing to that direction. And remember that announced fire perimeter to the east, that was exactly what we were seeing. So there's these multiple modalities of input that you can take advantage of and make the data a lot more accurate, or have a lot less uncertainty, or at least you can judge the uncertainty of the data if you use multiple modalities. And we had other partnerships starting after this. For instance, this is from the Lilac Fire in 2017 at the San Diego Fire Department. General Atomics, which is known for unmanned aircraft, they flew their King Air with infrared capabilities for us, or for the San Diego Fire Department, and we were using the perimeters generated from the aircraft to model the fire for Lilac Fire. And it was in real time, because we are generating those as geospatial services. They were in real time going into the state's scout system for situational awareness. Again, this could only be possible as this Spirit of the Heart partnership with the National Science Foundation support we received. So somebody had to put the R&D into it to build this, so we could start working on these scenarios. So the research and science could enable the operations, but there needed to be something to spark that infrastructure and support the building of the infrastructure. And this is what you see in then state's infrastructure. They have common operational models, so they can actually design evacuations and things like that based on the models. Thomas Fire. It was a huge devastation, and it had 4 weather events. Although we were used until then for initial attack, for Thomas Fire, when we were actually called for it, the fire was almost going into Santa Barbara. Right? They had like a thing that went into Santa Barbara. And there, the tool was used for running, backburn scenarios. When you burn this area, would the fire grow there? So what our users at that time, our collaborators, were doing is turn off the fuels to see if they burn that area, if the fire would move, or can they stop. So you can plan different response scenarios when a fire is happening if you had those tools in your hand as well. Just from the satellite detections that you're seeing here, you could see the devastation of Thomas Fire and how fast it moved in 4 times at a time. So what this means is the weather event started, and it had the first Santa-Ana event, beginning of December. Then the weather moved again. 1, 2, another weather event, and the 4th one will come and go into Santa Barbara. So the communities were here. They were evacuated 4 times in 4 weather events. So when the fire hit Montecito, they were already tired. And you know what else was happening? And it was known that it's going to happen. And other hazards were approaching. There was an atmospheric river coming on top of the area, and the huge rain falling from that atmospheric river was hitting Montecito. And that's indeed what happened, and debris flows caused huge devastation, with 21 people dying right after Thomas event. So I only bring disaster news, I feel like. In fall 2019, we are a part of a bigger state partnership. It was funded at $4.5 million level, the state, by the initiative of the Assemblywoman Coty Petri Norris to Orange County. So Orange County Fire Department received funding that the state prepaid a fixed-wing aircraft with infrared capabilities. And what we've done is we created a fusion center at LA Fire Department to respond to any fire, and the plane is already waiting on a high-risk day at an air base. And the moment a fire happens, the ignition point gets modeled by WIFIRE, and based on that, somebody decides that they need the aircraft up. It only takes a matter of minutes compared to hours before to get the permits running and the plane to be up in the air. And what we do is we constantly receive perimeters from the aircraft so we can actually adjust and finally build what we were told we won't be able to have. that fire information on the aircraft and being sent to us. So this is the Morea Fire. This is the ignition point. The blue marker there that you see, is the ignition point we received as the fire's ignition point. But when you actually go on the cameras, the pink lines that you're seeing are the camera we use. There are multiple cameras that can see this fire. When we triangulate and geolocate the fire, it actually becomes that red marker rather than the blue marker. So that approximation of the reporting of where the fire is, you can improve a little bit on that using the camera information that we are receiving. And it gets modeled, and based on that, the aircraft goes up and it starts sending us things like this. That's what it sees. And based on that, they get turned into perimeters, which goes into another industry partner, Intera, for common operating picture. And those perimeters, each gray line is a real observed perimeter from the aircraft. For each of them, fire gets modeled again, and adjustments get made based on that. And what happens is, from one of those perimeters, you have a fire model like that. It goes back into Intera for common operating picture integration. So that was the operational use, and what we didn't expect is the public interest. How much public needed information during these fires. And we've seen huge numbers of people coming to the site just for situational awareness. Just as a side point, we don't make public see anything predictive where the fire will be, because that only goes to the authorities who might or might not want to share this information at that time. But we make the public see where the evacuation zones are, red flag alerts, which is the high threat alerts, announced perimeters, weather, satellite detections, anything that they could find elsewhere, they can come to the site and view those during the fire. So in 2017, during Northern California fires, 800,000 unique visitors came in the course of the events of that fire, 8 million page hits. So it's a huge number when you think about it for small research site. And that type of use required on-demand usability and scalability. And what helped us is those original supercomputing concepts that we built this with. The system was built for scalability in containers and all kinds of things that you can actually turn on a switch and switch to the cloud, and in our case, our own more scalable environments. So, of course, we are not just operations. I said we have a lot of research going on in there. Today, I'm going to talk about dynamic scalability and what we are doing from edge to the cloud and high-performance computing environments. I'll also talk about inference pipelines to update some of these field databases, which we desperately need to be high resolution and more accurate. The things that I'm not going to talk about, the context. Not every fire model is useful in any environment. And when you ensemble them, you might get better results, but not everything in the ensemble you might want to run. Gridded weather models. In San Diego, our energy company said 2-kilometer resolution gives us a good representation of the weather. We can see all the phenomena. But when you go to some parts of LA, you won't see some of the calming effects in the valleys from the wind coming from the mountains until you go up to 1-kilometer resolution. So you spend more time, more effort to get those. So whenever you can avoid that, you need to avoid it. But when you need it, you need to have it. So that's what we call context-driven now. Not just data-driven, but using data and models in the right context at the right environment. And it requires building knowledge networks and things like that to represent the data and use of models, creating commons for models, just like we do for data, and things like that. And we have also become a data resource for a lot of environments like our utility is, and state and local officials on the side in this operation, and policy-driven secure data exchange and making things fair, open, but at the same time conformant to policy is, and operational and state programs is important for us. So first thing, continuous iteration and integration and doing data assimilation with it requires continuum of computing. I'm going to talk about a couple different efforts that enables us this. One is this new infrastructure called SAGE. And this was inspired by can we do some of these, fire detection or smoke detection or weather monitoring at the edge? And what Sage is doing, it's bigger than WIFIRE, of course, but it's very exciting to add sensing devices called waggles with accelerators, machine learning accelerators built into them, so that you can have computing at the edge with the right type of sensing associated to it. And you can do it in a way that's multi-tenant and scheduled for use of different models and different users to take advantage of this infrastructure. So its goal is to become the edge infrastructure at NSF's computing Continuum projects. And what Sage is doing is adding these waggle devices to HPRN's backbone. For instance, for camera sites, you can use the pan-tilt zoom cameras to do smoke detection or flash flood monitoring and other things in multi-hazards domain. And zoom into those areas and control these cameras if needed. Meteorological side, you can do extreme weather detection. You don't have to stream everything and do it on site. Seismic phase detection, there are seismic sensors on HPRN. So what we would do for WIFIRE, for instance, we could do inference at the edge, like on the aircraft. Instead of receiving the whole image, can we receive just a perimeter that's generated by a waggle device or an accelerator on the aircraft or on these cameras? That ignition point, when you're seeing the ignition point, can you actually do some of the processing there? And once they stream, the results of the stream on the cloud, you can do fire modeling, running ensembles, and things like that. We didn't do this in isolation. Over the years, actually, we had a few projects at UC San Diego, starting with the Pacific Research Platform, which then became Chase CI, that added GPUs across this 10 to 100 gigabit, very capable network. And these are single precision gaming GPU devices called Fionas with high I/O capabilities. And there, we actually worked on some of the techniques to bring, when you build this and manage things with Kubernetes and other type of more dynamic coordination middleware, you can actually integrate into other cloud environments as well. So what we've done in Chase CI was also adding some of these devices at the edge of HPRN, work some of these smoke detection and other techniques with our students, which we would hope to now do it in a more community-driven fashion with Sage. And where does supercomputing sit? I think supercomputing is becoming also continuum computing because there are a lot of scenarios like wildfires that can take advantage of both capacity and also the capability. I can have one part of the workflow running on an FPGA potentially, and the other part needing this highly capable exascale resources. So can we get there? What we call is composable systems. So Expanse will have the capacity of a supercomputer with some capabilities to do things like cloud burst through Open Science Grid and maybe using Kubernetes for scheduling extra resources like FPGAs and other new and upcoming architectures. So the heterogeneity concept will be used, and one of the examples for Expanse will be indeed WIFIRE, because you can think of doing those earlier fire, like Sage-like computing, JCI-like computing for big data and artificial intelligence on external infrastructure. But when you need that capability and cloud burst for running a fire model ensemble or high performance model, you can then switch to high throughput, high performance computing environments, like a cloud and supercomputing environments. And then you need to integrate model products, right? You're not stopping there. You're actually constantly collecting fire imagery, doing AI and machine learning on that. And you're also constantly doing data assimilation based on the fire result to reparameterize a fire model. The last couple of things I'm going to mention is this inference codes for, then how can you, when you do the computing, you also need the data to be the best. And actually that can be made a part of the workflow, or that could be taken offline, and you can generate new data, curate data when you can, or when you're on a regular basis, not in real time. So there are lots of machine learning case studies to curate those data sets, from prediction of the weather I showed today, or smoke detection. We even did some NLP type of studies to, can we understand radio communications about the local conditions firefighters are communicating, and turn that into data sets. But one thing we've done is classifying fuel data. And I want to emphasize, all of these machine learning type of operations still require periodic access to data. There needs to be programmability to repeat these, to run these on a regular basis. And having those APIs and models of the data itself become really useful when we try to do this. Shortly, how do we classify land cover, for instance? We get high-resolution satellite data from our partners. And these are digital globe and planet-like data sets that are 0.5 meter resolution. And then we turn those through some processing. We first tile them up for data preparation. And then we use some deep learning type techniques to actually extract features and classify these features. So you can create these histograms of tiles that are similar. And then you can weave these tiles, like some of them are short grass on some of these. What you get is those blue lines, like on the side, that becomes the related tiles. And then you click on each tile, the blue dots you're seeing on the map, or where these tiles are on the scene that was studied. So you could see different associations. Some of these will be some types of vegetation or fuel. Some of these will be the defensible space around houses. So you can use these for different types of modeling. Houses with, for instance, grass or trees coming on their roofs, which is a big burnable condition. But once you have these, you can use it for other scenarios. Wildfire prevention is good, but you can use them for land use, for urban development, for conservation efforts. So the techniques are, the data that comes out of these models, that inferred from these models, are useful, but techniques are also transferable. You know what we've done? We used similar techniques to map slums in Mumbai, India. We worked with UNICEF to look for schools in Liberia so they can actually make sure the sustainable resources were going to these schools that they might not be aware of. We looked at development of refugee camps with these techniques. It's all satellite data coming together with these inference type models, so they can be visualized. We can generate valuable insight from the same satellite imagery for different uses or different applications. So I want to end with acknowledging every infrastructure like this requires part data management, part data science, part domain knowledge or computational science in this case, and part advanced infrastructure. And lots of things were funded actually in the way of this by NSF before WIFIRE was even funded. HPRN was funded by NSF, and the satellites were funded by infrastructure that the government built. Kepler, the workflow system we used and built over the years, had a lot of government funding before this could happen. Farsight was US Forest Services, and the techniques developed for it, we developed in other projects, like we had DiscoSci for following oil spills with a dynamic data-driven way before that was funded as one of these projects. And all the infrastructure, all of those red or orange boxes, in that sense, are previous projects that was funded. So it's important, extremely important, to use what was built before. In SAGE, for instance, we are looking at many different existing infrastructure to make use of, to add that edge capability rather than rebuilding these. So I cannot say it enough that reusability of infrastructure and what we are building here, what we are discussing at this conference, is really important in the context of applications. And when you build something like that, it becomes bigger than the sum of its parts. It's a really highly subscribed word, but and it becomes impactful in many areas, and it can be expanded to many areas. And of course, a huge team was behind what I talked about today. Many other people, other than the friendly faces on this slide, and the numbers on the side you're seeing. And There's a lot of information on the web. News loves us, so that's why I put the C. And you can also I invite you to use some of this and work with us to take advantage of the infrastructure and the techniques. Thank you.
Thank you, Ilkay, for a fantastic talk. We do have a minute or two for some quick questions. I can't see anything. There's one over here on 2.
Andreas Gerndt from German Aerospace Center. Very nice talk. Thank you for your presentation. So I'm also coordinating a project on urgent decision making, and fire simulation or wildfire is also a use case. And we are wondering if we can add more sensors to the satellite data, to the in-field sensors, using social media, so Twitter account or something like that. If you get some messages from the social media, maybe you can incorporate that in your simulation. Did you think about that? Do you have some ideas about that?
Yeah, we looked into usage of social media, Twitter data initially quite a bit. And there's a lot of parts of WIFIRE that I haven't mentioned. For instance, overlaying in 3D environments, the fire models and the pictures we are receiving and what people are tweeting about it. And social media data has some problems with it because, the geolocation is not where the person is at times and things like that. So to get around it, because we notice people love to take pictures and post on Twitter, we built, for instance, a mobile app that was very experimental, so we could receive more information and stitch them together on 3D environments, for instance, together with fire maps. And we can strip the built environment with LiDAR type of data and apply. So there's been experimental projects like that. And I still think social media is a huge source of information. And one of the things we've done is also sentiment, where as the fire grows, how the public sentiment grows. Right? You can look into studies like that. We looked into public health type of scenarios, and if people are tweeting about it. And so there are lots of things that can be done with Twitter information, but it needs to be cleaned up, and we felt like it wasn't ready for prime time use yet. But it was a good research exercise for us.
Okay, I'm going to allow one very quick 1-minute question and answer on 4.
Yes.
You've got a minute for the question and the answer.
Thank you very much. You mentioned a lot about integration, legacy systems, heterogeneity. Now, how do you manage the risk of the reliability of the data or the risk of hardware which is trustworthy or not? Things will fail or not, but do you have a model to say how reliable is the information and the hardware that you deal with?
Yeah, short story is yes. And when you have multiple modalities of information, you can make use of it to check different data sets. And there's always an uncertainty attached to these data sets. And as we collect, for instance, this plane data, we are teaching how to automatically get that information and add that to the perimeter that we are using, for instance. For computing in Sage, there are some thoughts around how to actually rely on external information and resources.
I'm sorry we don't have more time for questions. Ilkay, thank you for a wonderful talk. On behalf of the General Chair, Michaela Taufer, we have a gift for you, and thank you very much for that.